Hi, and welcome back to these videos on support vector machines. So in the previous bunch of videos, we defined these support vector machines as basically linear models where you try to use the model that gives the maximum margin separating hyperplane. And just a quick recap, we formulated as an optimization problem, a convex one. We have a convex objective function that you want to minimize, subject to linear constraints, which are again convex constraints. And we saw this whole primal dual approach for convex optimization. And using this whole approach in the last video, we arrived at this alternative optimization problem for finding the maximum margin separating hyperplane, right? So you should, of course, watch that video before this one if you want to make sense of what we're doing here. So what we ended up with was this optimization problem. We have to choose these non-negative alphas to maximize this objective function up here, subject to this constraint that the sum of the alpha I, yi have to equal 0. Once we've solved it, we also saw that the optimal vector W describing the hyperplane that has the maximum margin will be found by computing this linear combination where you sum over all the training examples, take alpha I times the label yi times the feature vector xi. And finally, the offset B or the bias B could be found by basically finding the midpoint between the closest blue point and the furthest red point, the blue point being the +1 class, the red point being the -1 class in the direction of W. So this can be found by computing these two inner products and taking the average. Okay, so all of this is in the previous videos, so you should have watched those first. Right, and one important property that we saw by taking this primal dual approach was that we argued that these coefficients alpha I that appear in W in the definition of W, they're only going to be non-zero for the so-called support vectors, meaning the vectors that sit exactly on the hyperplane, on the margin. So you have these two blue points and then one red point that sit exactly on the margin, and only those will be involved in this linear combination. And we saw that this had some advantages when using it with kernels. Okay, so right, so in support vector machine, we find the maximum margin separating hyperplane. But if we have this data set here, right, this data set is not linearly separable, so there's not really any hyperplane that is separating. So of course, this whole thing falls apart. Whereas if you look at this data, right, it still seems that there are two clusters of data that are have a nice separation, and there's just these two outliers. What you could do, as we've seen in some of the previous videos, was that maybe you could use some feature transform, maybe a complicated kernel or something, high degree polynomial, to make the data linearly separable after the feature transform. But in this case, right, it doesn't seem that is the right solution, right? Because these just look like outliers. They don't look like things that actually are in the data, like things that you have to capture. So there's just a few noisy points, perhaps, and we'll see to try how can we deal with such few noisy points when we have a support vector machine. Right. And the basic idea is to use regularization as a technique, and in some sense allows a few of the points to be misclassified or perhaps have a smaller margin. So this leads to the following optimization problem. So what we see here is that the original optimization problem in SVMs tells us that we want to choose a minimum overall W, B, and just in the original, just over W and B, half the squared number of W, subject to these constraints, where we had that all these functional margins should be at least 1. Right, that was the original constraint. Now we add some slack in some sense. We introduce these psi i's, one for each of the training examples, where we allow, and these are variables too, and we allow these variables to, say, in some sense, subtract off a little bit from what you need to satisfy in terms of margins, right? So you can actually have a smaller margin than you're supposed to, than the most of the data. The idea is that you can have these psi i's, you can subtract off, and they're non-negative. And the basic idea is that in this minimization problem, if you're going to relax these constraints on the margin, so you're going to say, okay, I can let this point have a smaller margin than everyone else, then you're going to pay for it up here in the objective function. You're going to pay a factor C times this slack in the margin that you allowed, right? So maybe if the margin is only half as large as you would otherwise, if the functional margin is only a half instead of a whole, you'll pay a half times C up here. So it's a way to allow some of the points to have smaller margins, but you pay for it in the objective function. So this is a general regularization approach that will allow one to add such, have a few noisy points, right? So then this objective here, there's always a feasible solution You can just always make these psi i's large enough so that you can find a feasible solution to this optimization problem. You just have to pay for it in the objective function. If we did not have the psi i's and the data set is not linearly separable, then there might not be a feasible solution to this optimization problem. Okay, so basically the idea is that if the functional margin on the training example xi yi is psi too small, then you have to pay c times psi for that point. And this is still a convex optimization problem, right? We already showed before that linear functions are convex. So I guess this applies to the two types of constraints here. These are linear, so they're convex functions. Same goes with this additive term that we add up here in the objective. It's also a linear function. And the sum of convex functions is convex. So everything here is convex. So it's still a convex optimization problem. So we're probably in good shape. We can use some of these techniques that we saw earlier. So back to this regularized support vector machine formulation. Right? So what we'll do now is that we'll try to see, okay, what changes in the stuff that we did in the previous video if you try to write up the dual when we also have these psi variables. So for the dual, we first write down this generalized Lagrangian, the function L that we called it before, the generalized Lagrangian. It depends on all the primal variables, the variables that goes into the original optimization problem, W, B, and psi, as these are vectors of variables. And then we also have dual variables, one for each constraint in the optimization problem. So I guess alpha will take care of the n constraints on the margins, and R will take care of these non-negativity constraints. Right, so now we have to maximize first over the dual variables and minimize over the primal variables. This is the dual that we would get if we applied this convex optimization techniques that we saw before. And if we write out what is this generalized Lagrangian, right, it's the original objective function. So that's what we have here first. And then basically you get a term, you sum over all the constraints when you write them in standard form. You take the Lagrange multiplier alpha I in one case and Ri in another case and multiply it onto the function gi. And remember, in standard form, the constraints should be gi of x, or of the input variables, should be less than or equal to 0. So for instance, the second constraint here, you would subtract off minus psi I on both sides, so you get minus psi I less than or equal to 0, which means that the function that you would get is the minus psi I function. And this is the one that you have down here, the minus psi I times a Lagrange multiplier. So this is all just following what we did in the previous video. Okay, so this is the optimization problem that you get. And then, of course, we're going to use, as we did before, all these KKT conditions. We already checked that the Fs and the GIs are convex functions. And, well, the constraints will actually be strictly feasible because, well, you can always pay arbitrarily much in the psi i's. So we're all safe here. All these conditions are satisfied. So what we know now is that there will be an optimal solution. We can solve this dual problem, and there will be an optimal solution that satisfies all these properties, in particular that these partial derivatives with respect to the primal variables are going to be 0. Right, so I'm going a little fast because we already did some of it in the previous video. So let's try to do it here. So what we did before in the previous video was that we looked at this function and then we computed the partial derivative with respect to the Wj variables that goes into it. And if you see the terms that we have here, the only things that change, basically there's nothing that changes here, right? There's a Wj that we get from the partial derivative of this half squared norm of W, so that gives us the Wj. This term here has no occurrences of W, and neither does this last one here. And this one in here, we have the Wj is multiplied onto xij, yi, alpha I, and a minus. So that's what we get here. And this holds for all j. And if we write it in vector notation, this constraint that this has to be equal to 0, we get that w's should still be the sum from 1 to n of alpha I, yi, xi. So this is exactly the same as we saw in the previous video. Okay. So that's all the same. And we can also look at the partial derivative with respect to b. That's also something we did before. And we can see here, right, all the new terms we added, they don't include b. So basically the only thing that we have here is the same, exactly the same as we had before. So the partial derivative with respect to b is just, we have the minus, we have the alpha I, yi multiplied onto the b. So the partial derivative is just the minus the sum from 1 to n alpha I, yi. And we have to set this to 0. So that's the same as the sum from 1 to n alpha I, yi is equal to 0. Exactly the same constraint and condition as we had earlier. So that's all fine. That's all unchanged. And if we do the substitutions, the simplifications up here that we did in the last video, where we insert this definition of W here, and we insert this constraint and the sum of the alpha I yi's into this optimization problem, then we end up, the first part here is exactly the same as we had before. Right? This is exactly the optimization problem we had before adding these psi I variables. And then over here, we've just gathered the terms that involve the psi i's as a c times the sum of the psi i's, and there's a minus an ri times the sum of the psi i's. And finally here, right, there's a minus alpha I times psi I. So that's what we have here. So we just collected all the terms that come from the psi I, and the rest is the same as before. Okay, good. So, and of course, right, we had this constraint that we just saw before, where we had to set that the sum of alpha I yi has to equal 0. Okay. Good. So we, of course, we could also compute the partial derivatives with respect to these psi i's, and those should also be set to 0. That's one of these KKT conditions. So if we compute the partial derivatives with respect to the psi i's, if we look at this whole expression here, the only term we have is down here is this linear term. And with respect to psi I, you just get the single term c minus alpha I ri. And this has to equal 0, meaning that c has to equal alpha I plus ri. Right? That's all we're doing here. We're just setting this to 0. Okay, so c has to equal alpha I ri. And okay, so maybe one thing worth noticing is that, okay, in any solution where c has to equal alpha I ri, this whole last sum disappears, right? Because this becomes a 0. And so this whole term goes away. And so we can just move it. We know that the optimal solution has to satisfy it, so we can move it up as a constraint that c has to equal alpha I plus ri for I equals 1 to n. And now the term went away in the objective function here. So that went away. Okay, so what do we have now? What we have now, I guess, is an objective here that does not appear, that does not involve the r, right? We're maximizing over alpha and r greater than or equal to 0, but r is not in there. Okay, so this we can also use to simplify it even further. There's no r appearing. It only appears in these constraints down here. And r has to be greater than or equal to 0. And so does alpha. And now what you notice here is that, well, this thing here has a solution. You can always choose a non-negative ri, such that c is equal to alpha I plus ri, as long as alpha I is no bigger than c, right? For any alpha I that's less than or equal to c, we can choose ri to be c minus alpha I, then ri is going to be non-negative, and it doesn't appear in the objective function, so it doesn't have any influence on I guess, the optimal solution. So what this really means is that the only constraint we really need is that since the ri is not there, what we can do is we can substitute this last constraint that c is equal to alpha I plus ri by the constraint that alpha I has to lie between 0 and c. That's the only change, right? That's exactly what it means before, because we can always make it feasible whenever ri, with alpha I is less than or equal to c, we can always choose a non-negative ri that satisfies this equality. And we cannot if alpha I is greater than c. So this is exactly the same optimization problem. We got completely rid of the r, and now we just have these constraints that the alpha i's have to lie between 0 and c. Okay. And again, right, if we look up here, right, we have a minimum over w, b, and psi, and none of them appear in the objective function, and they don't appear in the constraints, right? So we can just get rid of them. And now we've arrived at the regularized version of the SVM optimization problem, just maximize over alpha, the same objective as we had in the previous video, where we did not introduce this penalty for things that do not have a large enough margin. And the only thing that changed, if you look at this as the original formulation, the only thing that changed is that before we required that the alpha i's were non-negative, now we further require that they're less than or equal to c, this penalty that we added on for not having a large enough margin. So that's the only change to the optimization problem, which is actually pretty surprising, that you just adding this penalty just changes this last constraint to also have an upper bound on c. Right? So that's the only thing that changed by doing this. Right? And we still, as we remember one of the steps, right, we still have the same. If you solve this optimization problem, the w is still the same. It's the sum of alpha I, yi, xi. Right? So if we solve this optimization problem, then we should just let w be this linear combination. Of course, you could ask yourself whether this formula for b is still valid. Right? So before we said, basically, if I know the direction of w, I should look at the closest blue point in the direction of w, the furthest red point in the direction of w, and then we should pick the b that shifts the hyperplane in between them. Right? And of course, this is not valid anymore, right? Because the closest blue one is this one up here, the furthest red is this one down here. And so this is, of course, not a valid thing anymore. So, so this is not the valid formula. So we need to do something else when we want to choose B. And this is basically at the level of an exercise. Like kind of the main idea is to, once you have the direction of W, you can try to place the hyperplane in between any two consecutive points in that direction and just sweep over them and find the right place to put your W, right? So this is something that you can work out the details for. It's not too complicated once you have the W. So we'll not go into detail with that here. Good. And the nice thing is, right, everything still works with kernels. Still, you just have W as a linear combination here. The only thing here is the inner product. So everything is still the same. We can replace this by the kernel. We can replace with predictions. We can apply the kernel between xi and the point x that we're making predictions on. And these are just constraints in the alpha i's. So nothing changed there. So that's nice. Now we actually know how to solve this regularized SVM problem, right? Where we add a penalty if you don't have a large enough margin. You can just pay a little bit in the objective value instead, with respect to C, where C is this hyperparameter that you can specify when you call the SVM. Right. Of course, this C is something that you as a user have to choose. And we already in a bunch of previous videos talked about using a validation data set for choosing such hyperparameters. So of course, you can do the same here, run the algorithm with maybe a bunch of different values of C and use the validation set to figure out what is the best choice of C to get the best accuracy on the validation set. Right. Now, I'm just going to end here with showing another alternative. Instead of solving this dual optimization problem, you can also do something else that might be simpler in some applications. So there's an unconstrained alternative here, right? We still have a couple of constraints that we need to satisfy and a convex objective function. Let me show you here that if I solve this optimization problem instead, so what is this one? This only has an objective function, no constraints. So what did I do here? So basically what I did here is I said that you're minimizing the same objective, except that in place of psi, you place in the maximum of 0 and 1 minus basically the functional margin. So what's the intuition here? If you think about it, the first constraint here, if you isolate psi, move psi to the other side, move the functional margin to the other side, basically get that psi is greater than or equal to 1 minus the functional margin, which is basically what we put down here. And also psi greater than or equal to 0 kind of corresponds to taking this max of 0 on this expression here. So there's some resemblance between these two formulas. And let me try to argue that if you can solve this optimization problem here optimally, you'll get the same optimal solution as if you solve this constrained optimization problem. Right. And if you look at this here, if you remember a couple of videos ago, we went through an example for gradient boosting, where we used the so-called hinge loss function. We use that as an example. This is exactly the hinge loss function. You take 1 minus the label times the prediction. Just no sign here, but this is exactly the so-called hinge loss function that you have here. So it's a well-studied loss function. Now, what we can do here is we'll try to argue that these two optimization problems actually have the same solution. And the way to see it is to say, okay, let's try to look at a W and a B. Let's say I picked a W and a B, and now I want to know, like in the latter expression, the unconstrained alternative, if I have picked W and B, this has some value, right? This optimization problem just gets a concrete value. There are no other variables. There's no psi down here. My claim is that for this W and B, if you in the top here, well, you fix W and B, and then you just pick the best psi that goes with it, the one that minimizes the objective value while still satisfying the constraints. Then my claim is that the cost of this solution in the top formulation will be exactly the same as in the bottom formulation, which means that the best you can do in both cases will be to find, well, the same W and B, because you get the same, for any fixed W and B, you get the same value of the two optimization problems. So the first one will also find the same W and B as the latter one, and vice versa. So, okay. So let's have a look at, well, if I fix W and B, and you choose psi now to be optimal for those W and B, what should you choose the psi i's to be? Well, if you already have a W and a B, you have to satisfy these constraints, right? That this left-hand side, the functional margin, has to be at least 1 minus psi I. and you pay by making the psi i's bigger and bigger, right? So the best you can do to minimize the cost is to set psi I exactly such that this is satisfied with equality, right? And of course, you're not allowed to make psi I negative, so otherwise you just set psi I to 0 if it would have been negative, right? So that means that the best choice of the psi i's are such that this equality is satisfied, or it's set to 0 in case this would require a negative psi I. Okay, that would give the optimal value here in the top formulation. Okay, now what is that value then? And you can try to see what that value is. So in the top formulation, right, the first term in the objective is the same as it is in the latter formulation. So what we have to compare is this second term, the c times the sum of the psi i's. So I guess we can start, and we have to compare that to what you pay down here in the unconstrained version for that w and b. You pay c times the sum of maximum of 0, 1 minus the functional margin. So if we look at this z times the maximum of 0 and 1 minus the functional margin, for this optimal choice of psi, the one you would get if you pick the optimal psi for this w and b in the top formulation, we just said that, well, these psi i's have to satisfy that this, if you move the psi I to the left-hand side, you move the functional margin to the right-hand side, you get psi i's equal to 1 minus the functional margin or 0. So this is exactly the same, right? This maximum of 0 and 1 minus the functional margin is exactly the same as the maximum of 0 and psi I. And the psi i's are non-negative, right? So this is exactly the same as c times the sum of the psi i's, which means that the cost up here is exactly the same as the cost down here in the unconstrained version. So for any fixed w and b, if I choose the optimal corresponding psi in the top formulation, I'll get the same cost as in the unconstrained alternative. So of course, these two solutions, these two optimization problems have the same optimal w and b. The costs are the same. Good. So this means that you can solve this unconstrained alternative. And if you look at what it is, this is actually a convex optimization problem. In here, you have convex functions. The maximum is also a convex function. So the whole thing here is a convex function. And for convex minimization problems, right, we know that we can use gradient descent, as we saw many videos ago. If you just do gradient descent on w and b, and this will lead you towards a global minimum. And so just solve this unconstrained optimization problem with the hinge loss here, or the penalty of c is the same as solving this regularized SVM version up here. Right? This is easy to implement. It's very efficient. You just need to know how to compute the gradient, and this is not so hard. We already saw that basically in deriving in these things we did with the dual. And well, the only downside is that this does not work with kernels, right? Because you're doing gradient descent on the individual coordinates of w. And if you think about it, if you've done a feature transform to higher dimensions, w has a parameter in for every coordinate in higher dimensions, has d prime parameters, and these are the ones you're doing gradient descent on. So this is why this does not work with kernels, right? And that's the main downside. That's why you would actually, in many applications, if you are going to use kernels, you will probably prefer the first formulation of the problem, the one that went through the dual. But if you don't want to use kernels, then just gradient descent here would be a very easy alternative for this. Good. So basically what we need to be done is to show that we can solve this dual problem even when we have kernels. And that's all that's left. And this is basically, we'll describe the main ideas in an algorithm for doing so in the next video.